we do this. This is the so-called Friedberg-Muchnik theory. And just like this low simple set, so this gave us the first example of a purposely constructed set in between computable and jump, even though we had one before. This was one we did on purpose. Friedberg-Muchnik shows that there are incomparable sets between, there are incomparable CE sets. So that's exactly what it says. Exists AB computably enumerable that are of incomparable Turing degree. But we did construct incomparable sets before, but at the time we didn't bother to make them CE. But of course, from this earlier effort, we know exactly what the requirements should be, because we came up with requirements back then. And so requirement RE is A is not equal to phi EB if E is even, and it is B is not equal to phi EA if E is odd, and this is of course a funny way to subdivide it between even and odd indices. Is there something deep and inherent about our coding for Turing machines? Well, certainly not, and even to make this sensible, you might have to tweak your coding for Turing machines a little bit. We want the RE for E evens to take care of all Turing machines for A not being computable from B. And we want the RE for E odds to take care of all Turing machines so that B is not computable from A, and there's a little bookkeeping in the background to then be able to write it down like even and odd. A lot of what we do is concerned with getting the bookkeeping to work. At the same time, I hardly ever go into quite enough detail to get to the point where it might matter, which I certainly don't intend to do today either. So what did we do before? Well, before when we had this, we constructed by initial segments. And we said we have some initial segment of A, we have some initial segment of B, and now we're going to look for the next element that hasn't been determined yet for A, whether it should be in or out, and check whether we can extend the approximation for B in such a way that we get different values or not. And then we acted accordingly to make sure that if there were no different values available, then whatever was computed here would be computable, right? If you couldn't extend the oracle in any way to get a different outcome, then whatever is computable by any extension of the oracle is computable by just searching for extensions. And in the other case where you had two things which had different values, then, well, if they have different values, then you can choose, then in particular one of them is not equal to 1, and then you can choose this one to be different from that one and extend in that way. So the big problem compared to with this theorem is we want these things to be CE, and so we need to be a little bit more effective. But of course we know exactly how to get things to be CE, because you get things to be CE, our big CE method, do computable stuff until things look good, and then enumerate into A or B. And then do some more computable stuff until you accidentally find the right things and enumerate into A and B. Right? So we know how to make things CE. Our method needs to look like do computable stuff, enumerate into A, do computable stuff, enumerate into B. Okay, so that's what we're going to do. First, of course, the basic module. We have our requirements. How do you take care of a requirement at all? Okay. So these requirements are, of course, completely symmetric. So if we have a basic module for one, we have a basic module for both of them. So we're going to just start with a basic module for A not equal to phi EB. Right? How do you do this? Well, the way you do this is you choose an x which is not in A. Right? If x is already in A, then there's nothing you can do with this x. So this is an x where you still have some freedom as what to do. Well, you know exactly what your freedom is too. At some later point, you can decide to enumerate x in there, and then you'd have to be done. So this is it picks this x, and now wait for phi e of b of x to converge to 0. Right? So what does this mean? Right? The construction goes along in stages. At the first stage, where this basic module becomes active, you pick this x, which is your diagonalization witness, and then at future stages you check whether this happens. If this doesn't happen, you don't do anything. If this does happen, then it's time for action. Notice that if this doesn't happen, you've won. Right? If this computation never converges and goes to 0, then the fact that this x is not in A is exactly the right thing. Because if this were the characteristic function of A, then it would have to converge and give 0. Right? So if you go into a wait stage, you're all good. If this happens, then the action is also pretty clear with the things we've done before. Then we enumerate x into A and restrain phi e b of x. Right? If this computation ever converges to 0, then we can say, oh, okay, now for a moment it looks bad because both of them are 0, the characteristic function and this thing, but one of them we can make 1, and then we can do our best to keep the other equal to 0. So for any such module, you have these two outcomes. Either you wait forever, or you diagonalize. Right? And by diagonalize, I mean you take this action. Those are the two possible outcomes of this basic module. And clearly, the basic module in isolation works. Right? Because either you keep waiting forever, or at some point you enumerate and protect, and if your restraint succeeds, right? If the B doesn't get changed below this restraint, then this will be forever preserved, and you've succeeded in making A different from phi of B. For the other requirement, of course, exactly the same happens, but now you pick your witness x in B, and if you ever see phi of A converge to 0, then you restrain A for a while. Okay, so now we need to look at this. How can we make our basic module work well with respect to other things? Right. Well, how does this basic strategy possibly injure other strategies? Well, the only way other things are injured is if their restraint is not satisfied, and their restraint is not satisfied if something goes into the set they're preserving which is too small. So this X, which you pick and then keep out for a long time, but when you pick it, you know that you have the intention of possibly enumerating it at some point later into the corresponding set. So the right way to make this basic module work nice with respect to the higher priority arguments is to choose this X bigger than current restraints. With then, in the background, I didn't say this, bigger than the current restraints of all higher priority requirements that put restraints on A. It doesn't actually matter if you also consider the restraints on B, but those are the only ones you care about. Then we're essentially done. Now, why are we essentially done? Well, because if you look at this basic module and you notice that we already analyzed, if this basic module does not get injured, then it succeeds at satisfying the requirement. Moreover, if it succeeds at satisfying the requirement, then either it imposes no restraint, if you stay in the wait state, or it imposes this restraint. And once it no longer gets injured, then once it imposes this restraint, it will forever impose the same restraint, and therefore its restraint stabilizes. So now with that analysis, the proof goes through exactly as before, where you say, okay, we're going to do, of course, an inductive proof. The inductive proof shows that requirement RE is satisfied and that the restraint imposed by requirement RE stabilizes to a fixed limit. By induction, you presume that this is true for everything that comes before. And maybe, just for simplicity, you might presume that every requirement acts only finitely many times. Because if you assume that, then you can say, okay, now that I've assumed all these things, by induction I can wait for a time t when all of the higher priority requirements have done their acting, if they will ever act, and all the higher priority restraints have stabilized. Because the acting and the stabilization happens at the same time, is actually the same point in time when this happens. And then, I forgot to say something which I should have said. You choose your X bigger than all current restraints if now one of the higher priority strategies gets injured by an even higher priority strategy, then its corresponding restraint might increase. And that might mean that the witness you picked might now be below the restraint of a higher priority requirement, but you can see that this happened, that this X is now smaller than the restraint of a higher priority requirement, and then you just need to discard your current witness and pick a new witness which is above all the restraints. So the reason I realized this at this time is because I was arguing, okay, pick this time t when all of the higher priority things have acted and have had their restraint stabilized. Either the witness you now have or the witness you now pick, right? If your witness currently is too small, then you enlarge it once, or it already is fine. And this witness is now forever an acceptable witness because all the higher priority restraints have stabilized, so they will never increase past your current witness. And therefore, either this never happens, and your requirement is satisfied with forever zero restraint, or this happens at some point in time, you enumerate this element in and you impose this restraint, which now stays the restraint forever. And then finally I overloaded a little bit the induction hypothesis a little bit, saying that every requirement acts only finitely many times. Right? In the argument I just gave also I said you enumerate this in and then you're done forever. So this is then a time when you've stopped acting and therefore you act only finitely many times total. It all works out.
How do you know this only finitely many times things get injured?
It's by induction. I presume that everything acts only finitely many times. Or my induction statement is, for all requirements less than E, they act only finitely many times and their restraints stabilize. And then I look at E plus 1. And so for E plus 1, I presume that I go past the time where everything has acted, and then it will no longer get injured, and then it acts once more, and therefore it also acts finitely many times, stabilizes, and everything.
So you just start with the base case and there's nothing below it?
There's nothing below it. The requirement 0 never gets injured. You have a pretty poor construction if the requirement 0 gets injured, right? There's actually an interesting bit of bookkeeping which I secretly kind of introduced here, but not very much. And this is that if you look at this construction in the right way, then there is a tree in the background, and this tree tells you kind of what happens. So let me, I don't want to describe the full method on the tree, but I just describe the tree a little bit because I do want to say more about the so-called tree method later, and I'll prime your brain for it. So we have an infinite sequence of requirements. Each of these requirements has this basic module with 2 possible outcomes. So as I'm going along, let's say at stage S, right? Stage S has S substages, where at the first substage I do my work for requirement R0, then at the second substage I do my work for requirement R1, and this way, right? So at stage S I look at the first S requirements, and I perform a step in their basic module. Or right, check what's going on. So what happens is that now I can draw a picture. This is that's the picture. A full binary tree labeled with diag and weight, and let's presume that diag is less than weight. But you have this full binary tree. And on this tree at stage S, you do these constructions, and you can tell what happens. You can say, okay, R0, this is level R0, level R1, level R2. Right? We have our requirements ordered in sequence omega, so the 0th level corresponds to R0, the first level corresponds to R1, the second level corresponds to R2, and onwards like this. And now at say stage S, I can say, okay, R0 is still in weight stage, R1 has acted and diagonalized, and R2 is still waiting. So this is sort of an approximation. This would be, say F2 at the second stage. It's an approximation of the record of what has acted so far. And now what did we notice? At some point I kind of forgot this because we weren't doing this on the tree, but we noticed that if R naught acts and imposes a restraint, then our higher priority strategies should consider picking a new witness. Right? So now you can see this very nicely on this tree. You can say here at this node I have a strategy working on R1, and it has picked a witness and is doing its stuff. But now, as soon as R not acts, then our approximation of the pattern of things which have acted so far would change to go to the other side, right? R not would go from wait to diag. It would act and change its outcome. And then we can associate to this node just a completely fresh basic module for R1, which starts, picks a new witness, and goes on like this. And then here, right, it initially goes into wait state, and the things after it are probably in wait state. You don't know because maybe something immediately converges the first time you check, so it might go into something else here, might go into diag state already. And this way you have a nice overall organization on how your basic modules act. Every node in the tree has a basic module associated to it, and this basic module starts becoming active if this path, this current approximation, passes through it. And now you notice a couple of nice things about the path through the tree, such as it only goes left. Your tree here only moves left. Some requirement acts and moves the tree left, or moves this path left, and then you continue on like this. And so you only move to the left, and you get longer and longer approximations through this path through the tree. And because you only move left, you get that this path has a limit. This limit of the path is known as the true path. And now you can argue in a way similar to what we did before, where we said, well, by induction we presume certain things happen, and then we let t be the time when these things have happened. Now you can argue very similarly and say, let t be the time when a sufficiently long approximation for the true path agrees with the actual real true path, and then look at what happens from that point on. And that is, if you work through the details, which is a good idea if you think about these things carefully, then you'll notice that the argument in this proof is very much the same or similar as the argument we gave here, the inductive proof. But you have some nice bookkeeping in the background, which in particular will be useful when you start doing more complicated constructions, where maybe the path doesn't always move left, but sometimes it also moves right, and then you can these are complicated constructions which I don't want to sketch right now, but this is a handy bookkeeping device that often works well in priority arguments, known as the tree method. And I'll say more about that later. But this is a nice first situation to give a sketch.
Does it matter which way it moves? If you're looking for a true path, you can just use compactness, right? I mean, it wouldn't matter how the tree moved eventually.
Well, but it gives some nice things, right? We didn't analyze this yet, but what is IE, the number of injuries, or an upper bound on the number of injuries of the ETH requirement? So if you
2 to the E, right? Because you can sort of click the thing over 2 to the E times and make it all diag.
exactly. And that is exactly the upper bound you get. Now of course, without the tree you can argue the same upper bound because you just right? Do the usual thing. You guess that the bound is 2 to the E. Where this guess comes from you don't know. But then once you've guessed this bound is 2 to the E, then you do the inductive argument. And in the inductive argument you get, well, suppose we are at the stage where R0 has not acted yet, then it's just the number of injuries caused by R1 up to RE, which is 2 to the E. Then R0 acts, everything gets initialized, and each of those get to act again. And now I have 2E plus 2E, which is equal to 2E plus 1, which is exactly the inductive argument you wanted.
Well, I mean,
But from the tree, it's pretty much needed.
well, I mean, not just for this argument, for anything we're going to do. I mean, is that how true paths work, and we have to use the compactness? I mean, let's say IE was infinite.
Well, a priori, you could certainly imagine an outcome which fluctuates infinitely much.
But you have a subsequence that doesn't. You know?
You have a subsequence that doesn't.
You know? I mean, would that be a true path? I mean, for some sort of infinite.
Yeah.
Okay.
Yes.
Yeah.
Yes. But you want the fact that it moves left is conventional. If the true path keeps fluctuating, then you look for the lim sup or the lim inf, whatever is the leftmost thing which occurs infinitely much. That is the path you care about. Because right, this being a finite injury construction, we don't really need the tree. Right? We were able to do it just as well with it being linearly ordered. But on the tree you can now say certain things like this node, it gets to do whatever it wants as long as it's nice to the things which are to the right of it. That's totally wrong. As long as it's nice with respect to the things which are to the left of it, because the path might move left later. Anyway, so it's always hard to talk about a construction which we aren't currently doing, because it's kind of hand-wavy, right? But I hope I described, at least for this construction, well enough how you put it on a tree. And that is 2 to the E became totally obvious because of it. Everybody happy with it? Okay. Okay. Next construction. For every non-computable CE set C, there exists a simple A such that C is not below A. You've seen a lot of simple set constructions, but this one really shows that right, in the picture of all Turing degrees, whenever you take a CE set, C, and its upper cone, it's a picture which in many ways is very similar to just the whole picture, but outside of this upper cone you can find the simple set A. And to a large extent the key of the key part of this argument is how do you avoid a cone like this at all? How do you avoid A somehow computing C? turns out there is a really cute argument for this. Okay, what do we want? Well, we want A co-infinite and satisfying NE C is not equal to IE of A, and PE, if WE is infinite, then WE intersection A is not empty. Now you look at the second requirement, or you look at co-infinite, we know how to do co-infinite, right? It takes sufficiently long initial segments of the approximation for A, where there is some stuff in the complement, and stop messing with it, right? Parts of the complement need to stabilize at some point. And we know how to do this. There's restraints that you just need to impose at the right times, and everything works out. PE we also immediately know how to do, because what do we do? Well, WE is infinite. We wait for some witness to appear. If this witness appears, then you enumerate it into A. And you also know how to make this act nicely with respect to other things, because you wait for a witness to appear above the restraints. And of course, in this construction, as in any other construction, whatever restraints we impose, they have to stabilize and become at a fixed location at some point. And if that happens, then something bigger will appear if it's infinite and can be enumerated. This is different. But what would you want to do? Well, you would want to if you look at the previous argument, you would want to say, well, take an x, which is not in C, and wait for this to go to 0, but C is not you, C is the enemy, right? You don't have control over what happens with C. Now, of course, if at some point you see something in C where this computes 0, then you could, from now on, protect A, and you've made them different. But if this is 0 in some place, and this is also 0, then, well, you can't make a 0 into a 1, because this Turing machine is... What are the chances you can find something like that? And right? That's just not the right strategy to try and change the oracle to get something desirable to come out of a given computation. It doesn't work like that. So I guess what I argued is co-infinite and PE requirements are easy enough. We understand those. We know what to do. This NE requirement is the requirement that we need a new strategy for. Now, the strategy turns out interesting and a little counterintuitive, because what are we going to do? What we're going to do is we're going to look at initial segments of C and phi E of A that agree. And when we find an initial segment that agrees for some bit, then we're going to protect the A side of it to never change again. So the strategy essentially amounts to, instead of working very hard at making these two things different, we're going to work very hard at preserving whatever agreement happens to occur. Now I'm purposely lying a little bit, but this is essentially the strategy. Why am I lying a little bit? Well, so we define the length of agreement at stage S to be the maximum of x such that for all y less than x, phi E S A S of y converges and is equal to C S of y. and then we define the restraint RES to be the maximum of the uses x for x less than or equal to the length. And now you look at this, so this length of agreement, this x really measures how far out these two are equal at stage S. And the restraint protects all of the computations that are involved in this equality plus 1. Right? This is less than or equal to the length of agreement. This length of agreement is the largest x such that everything strictly smaller is the same. This is what we do. Right? Our basic modules for NE are now clear. At stage S, you compute what is the length of agreement, you compute what is the corresponding restraint you want to impose, and you impose this restraint to all lower priority requirements. Then PE works in its usual way. PE just says, well, wait for an x which is in WE bigger than all previous restraints, and while WE intersect A is not empty. This last requirement, again, to make sure that every requirement acts only finitely many times. And if you find such an x bigger than all restraints, enumerate it into A, and then you're permanently done. The cofinite part, just like before, look at where a particular marker on the complement is currently and impose the restraint that nothing gets to be enumerated below this marker, and that will always satisfy. So that's the construction. Right? We have our basic modules, we have seen how they interact with each other, and now we need to see that they work. Well, again, inductive proof, suppose that all the requirements before the given requirement you're looking at have stabilized their actions, have enumerated what they have to enumerate, have imposed the restraints that they want to impose, and have achieved final and permanent values on the restraints they impose. So this means that now the current requirement you're looking at can almost work in isolation, because all the higher priority stuff is done working, and all the lower priority stuff will respect whatever it wishes. Now, if this is the cofiniteness requirement, it just imposes the restraint and is done. If this is a PE requirement, it waits for a large enough x to appear, and then it enumerates, and it is done. If this large enough x never appears, it doesn't do anything, and it's already done at this time. If it's an NE requirement, it just keeps computing these lengths of agreement and imposing the restraint. And so now we have some work to be doing, because we want these two things to be different, but all we're doing in the construction is waiting for a certain length of agreement to appear, and then we protect this agreement, which seems a little bit off. Right? But what happens? So now I'm going to argue that if we do our strategy like this, step 1, the sets will be different in the end. And then step 2, well, if they are really different in the end, then at some point this difference becomes clear, and then this difference will forever be preserved, and therefore from the point of time that this difference appears, the length of agreement stays fixed, and the restraint stays fixed, and everything stabilizes. So that was a little quick, but I'm first going to do the other argument to show that they're different. what's going to go into the argument that are different? Well, what have we used? We have used that our set C is a CE set, but we have definitely not yet used that it's non-computable. So the non-computability comes in now. We're going to assume that, well, suppose even when we follow this strategy for constructing RA, it turns out that C is equal to phi E of A, then we should be able to prove that C is computable. Right? Because what happens, well, if C is equal to phi EA, what follows from this? Well, in particular, it follows that the length of agreement goes to infinity, right? Because both A and C are CE sets, so they have these increasing enumerations. So initial segments of C stabilize at some point. I don't even need to be CE for that, just delta 2 is enough. And because this is equal, this is a total Turing functional, so for every input it only requires a finite part of A, and any finite part of A will eventually stabilize. And so, if this is true, then the length of agreement goes to infinity. But now, what happens, right? We have sort of the phi EA side and the C side, and they agree for a little bit. This picture is probably going to be bad, but I'll do my best. What are these things? This is like initial parts of the characteristic function, and they agree for a while. But now, what happens is, as soon as we see this agreement, we protect the A side. Right? We are past the point where this requirement gets injured, so this requirement never gets injured, therefore whatever it wants to restrain is in fact restrained. And that is to say, whatever happens on the A side, once we see this agreement, this part here is preserved forever. Well, if this part here is preserved forever, and these two things are equal, then we know what C looks like up to that point. Okay, so here now is the way you compute C from the current information. You start running this construction, you know the limit goes up to infinity, and you want to know what is C of x. Well, in order to find out what C of x is, you wait for this limit of agreement to go past x, and then you see what the value is at x. And this value at x happens to be at both sides, and because you forever will preserve the value of x on the A side, that is the final value under these sums, that they are equal. Therefore, because C is not computable, we can conclude that C is not equal to phi E of A, and the end of the hour couldn't come at a worse time, because the remainder of the argument is too long to finish now, but I'm going to have to say a lot of the same things again on Friday to actually finish it. But everybody happy with this argument? Okay, I'm going to do it mostly again on Friday anyway, so...